here. Today, we'd like to go over a few of the myths and dispel a couple of the misconceptions about 5G. But first, a bit of a refresher course about what we're talking about. 5G is a new cellular plan that operates not just in the original CDMA and GSM bands of 900 megahertz and 1.8 gigahertz, it also works in the newer 3.5 gigahertz plan, much to the consternation of a heck of a lot of people in the satellite communications community that used to use that band a lot. You might want to keep that in mind because that band's been around for about 45 years. The next bands that everybody's worried about and the things that they're talking about right now are the KA bands, 27 gigahertz, 37 gigahertz, 29 gigahertz. These are the ones that have everybody worried. So, first to the refresher course. OSHA sets a limit for good dry erase pens of maximum exposed power level, unlimited exposure for any human body of 0 dBm per centimeter squared. That means for any 1 centimeter of your body, 0 dBm is the maximum that OSHA allows. Now, OSHA defaults to ANSI, the American National Standards Institute, to derive this specification. Now, this counts for cell phones, radios, telephones, or anything else. Unlimited exposure, any human body, 0 dBm per centimeter squared. What 0 dBm means is 0.001 watt of power. As an example, your microwave puts out anywhere from 1,000 to 1,600 watts, depending kind of on how affluent you are. But this also depends on frequency, F, because frequency determines wavelength. Now, as far as wavelength is concerned, the higher the frequency, the shorter the wavelength. Therefore, you can, at higher frequencies, actually put all of your power into that 1 centimeter. At lower frequencies, if we start with a frequency like, say, 3.5 gigahertz, 3.5 gigahertz has a wavelength of 4.0 inches. So 4 inches squared equals 16 inches of area. So even if you had 1 watt of power coming out of the thing, so 0 dBm at 3.5 gigahertz is going to be spread across an area this large. And if you look at any 1 centimeter of that, which means you're going to divide by 4 times 2.54 times 4 times 2.54, you're going to get a whole lot less power per centimeter squared, comfortably under OSHA's limit. And I'll keep trying to find a good dry erase pen. Yay. When you get to 35 gigahertz, that wavelength becomes 0.35 inches. That same 0 dBm is all going to be concentrated in one small spot. One of the things that's important about all modern cellular technology is the shielding that they build into it. And the reason why they build the shielding in such a way is so that the antenna face is on the back face of any of these cell phones, whereas the speaker is on the front face. There's a shield in between the two of them. This means when you're talking on this silly thing, your power is radiating out and away from your head. So we'll start with that. This allows them to crank up the power a little bit more to 10 milliwatts. But what's received back here is 20 dB down. That's backlobe energy, and that's going to be addressed in a different video. We'll talk about front lobes, back lobes, and antenna designs separately. For now, what you have to know is that if you're putting out 10 milliwatts here, even at 35 gigahertz, you are getting not 1 milliwatt, but 0.1 milliwatt, or 1/10,000th of a watt. That's one of the first things I wanted to address. We'll talk about 35 gigahertz shortly, but next we want to talk about free space path loss a little bit. All right, so again, in another video, I'm going to be talking a lot more about free space path loss, but for now, just generally to let you know, the equation for this one is 10 times the log of wavelength squared divided by 4 times pi times distance squared. And that actually gives you the amount of loss that you have. And you can do this on any spreadsheet, any calculator you need if you want to find out how much power you're actually seeing from any transmitting source. It's a handy thing to know, and once you get it, we'll go through one next video, but for now, just to let you know, at 3.5 gigahertz, and I'm going to use my handy dandy cheat sheet here, you lose, in 12 feet, you lose 54.6 dB. At 6 feet, let's just go down to 1 foot. It's 1 foot away from you. At that point, you only lose 33. That's how much power you lose. That means that is a factor of 2,000. 2,000 times less power is hitting you than was at the transmitting source. That's a function of, let's say, for some reason, you jimmy your microwave open and you're letting 1,000 watts spill out into the room. That's 60 dBm. You lose 33 of that, now you're down from 60 dBm, which is 1,000 watts, down to 27 dBm, which is a half a watt. So you've got a half a watt at 1 foot away, still way outside the OSHA limits, way too high. So you need to get a little further away, or better yet, don't jimmy your microwave oven open. Probably a safer bet. And here you see a chart of what 1 watt looks like, a tenth of a watt, a hundredth of a watt, and a thousandth of a watt, which is our reference level of 0 decibel milliwatts. This stands for decibel watts. So that's about it for now. Thank you for being here. Path loss, as I tried to explain, hopefully successfully, varies by frequency because it varies by wavelength. That, by the way, is the symbol for wavelength, lambda, and so as frequency goes up, path loss also goes up for any given distance. So the higher the frequency, the more path loss you're going to get. Wavelength, since we're here and the question was asked, is its own calculation, which I think I'll just do down here and leave this other stuff up for a few seconds. Wavelength is equal to C divided by F. Now, interestingly, C divided by F can be expressed in several different terms. C equals the speed of light, equals 186,282 miles per second, also equal to 9,985,000,000 feet per second, approximately. Also equal to 11.803 inches per second, 11,803,000,000 inches per second. Now, that's a handy number to know, especially if you express it in scientific notation as 11.803 times 10 to the 9th, meaning billion. Because from this, since your frequency, and let's say in this case, F equals 4 gigahertz, which equals 4 billion cycles per second. So since you've got 11.8 billion of these and 4 billion of these, both of them are already in the billions, so this function becomes 11.803 divided by 4. And that will give you your wavelengths. Again, thanks for being here. We appreciate you taking the time, and we'll get back to you soon with a new video.